Okay, so in this video, I'm going to talk about the secant method, so a slightly different line search method, and then I'm going to summarise the line search methods in general. Okay, so there's a bit of an issue with Newton's method in the way that we presented it, in that we have to know a bit more information about our function. So as well as knowing the first derivative of the function, we need to know the second derivative of the function as well. So we have to be able to write this thing down analytically and then differentiate it twice in order to be able to apply Newton's method. And that's a bit of a limitation, because we've talked before about how you might not always know what the second derivative of the function is. You might not even be able to differentiate the function in the first place. So knowing f double prime of x is quite a limitation. And so the question is, what do we do if we don't know the second derivative? So if we need to approximate that. So there's quite a simple solution to this. So I've written Newton's method up on the board here. And the problem is, what if we don't know f double prime of x? And the thing that we can do if we don't know f double prime of x is we can just approximate it. So we can write we can approximate f double prime of xk by, well, you know, the formula for the gradient of a straight line. Right? So we've, if you think back to the formula for the gradient of a straight line, well, what do we do with that? So here I would approximate this by a couple of different function values. So f prime of xk, subtract another value for another function value here. So let's pick the previous iteration, right? So we've got two different points on this curve. We take the difference between them, so that's like the rise, and then we put this over the run, so the distance between these 2 points along the x-axis, so that's xk, take away xk minus 1. So the two previous iterations we can use to approximate the gradient of f prime of x, or the second derivative of fk. And then all that we do to get our secant method here is, if I have this approximation here, then I can just replace that in this. So my scheme can become, instead of dividing by f double prime of xk, I divide by this thing and divide that by f prime of xk, take away f prime of xk minus 1. Put that there, and then this becomes the secant method. That's all it is. So really, the secant method is just a fancy name for taking Newton's method and then approximating his second derivative. So that all I need to know here is an approximation. All I need to know is the first derivative of my function. And then I can approximate the second derivative, and I can run something that looks a lot like Newton's method. So that's the solution. Well, that's a solution. And what it looks like, pictorially, is this. So if I've got two guesses at where my minimizer is, so I'm looking at, I'm thinking about Newton's method in its sort of root finding format here. So if I take xk and the previous iteration, xk minus 1, right, I can evaluate f prime of x at those two values. I get these points here. And then all I'm doing with this secant method is approximating the gradient of the curve by the slope of the line connecting those 2 points. So I can calculate that sort of using high school math. That gives me a slope, and then I can evaluate my function. You know, I can figure out where that line crosses 0, and that becomes my new approximation. So this point here, xk plus 1, becomes my new iteration. My new approximation. And then I take xk and xk plus 1, approximate the slope of the line between those 2 points, and then keep doing this process again and again and again. So it's really Newton's method, just where I'm approximating the second derivative. That's all. Now, there are a couple of disadvantages with this, which I should make sure to mention. So the first thing is that I need two different starting values. So instead of just making an initial guess at the solution, x0, I need to make two guesses, x0 and x1. And if I choose those badly, just as just as Newton's method could diverge if I chose x naught badly, if I choose x naught or x1 badly, then the secant method can diverge as well. So it's a bit more risky like that. So here's an example. So this is one that we looked at for Newton's method before, where we thought that Newton's method, if you think of it as a root finding method again here, would diverge because successive lines would intersect the x-axis further and further to the right. And you can see that that's going to happen with the secant method as well. If I put a line between these 2 points and approximate the gradient using that, then that's going, that line's going to cut the x-axis further and further to the right. So this is going to diverge away from the true root, the true location of the minimum of f of x there at x star. So Newton's method and the secant method will both diverge. Here's one where Newton's method converges, right? Because if I imagine starting at this point x naught here and taking tangents to the curve, right, and fitting, and then imagining where those straight lines, where those tangents to the curve cut the x-axis, then you can see that those lines are going to get closer and closer to x star. But the secant method here is going to diverge because if I put a secant through x naught and x1 here, then that line's going to hit the x-axis way out to the right there. So that's a case where Newton's method will converge, but the secant method will diverge. So that is that's the risk with using the secant method. Of course, if x1 was chosen to be back here, the secant method could work quite well, right? A secant through those points is going to cut close to x star. Yeah. So that's the secant method, and that's it. So, so there's one other disadvantage, which is that this takes some mathematics to be able to prove this, more mathematics than we want to do here. But it turns out that the order of convergence of this secant method is, actually involves the golden ratio. That number, root 5 plus 1 over 2, is the golden ratio. So it has an order of convergence that's a little bit slower than that for Newton's method. Right, so not as bad as the dichotomous search or the golden ratio search, direct search we talked about before, but slower than Newton's method. And if you're interested, you can go back to this paper from 1973, if you like, and look up the fascinating proof of that. So the secant method has some disadvantages, but it requires us to know less information about the function than what I did before. So that's it for line search methods. So here's a summary of a few different line search methods. So the most general type of line search methods that we have are ones where I assume nothing about f. All I use is f, and I don't even have to assume that f is smooth. Right? So f can be whatever it wants. It doesn't have to be a smooth function. And I can use either the dichotomous search or the golden section search or the Fibonacci search, if you look up what that is, to optimize those functions, to find the optimizer of those functions. So they're relatively slow, relatively inefficient, each of them. We've talked about why. But they assume nothing about f, which is quite powerful. Then next, if we have a smooth function, right? But if I don't assume anything else about it, then I can use this quadratic search method, which is called the DSC algorithm. So essentially, you fit a quadratic to your function f, and then find the minimum of that quadratic all the time. And then if I know a little bit more, if I know f prime, I can use this secant method because I can approximate the second derivative. If I happen to know the second derivative, right, so my function f has to be smooth there, then I can use Newton's method, which is sort of the king of all of these. It's sort of the fastest, that order n squared, that order 2 convergence is actually quite fast. So that's it. That's it for line search methods. There's a variety of things to choose from, and they're really useful tools.